Okay, as promised, I'm making a video cast of organohalide chemistry, along with hopefully with other topics. Okay, so for organohalide chemistry, you've seen aspects of this chemistry before. We talked about substitution of alkanes. We've talked about chlorination of alkenes. So you've seen elements of organohalide chemistry previous to this, and some of the reactions of organohalide chemistry, for instance, formation of ethers by substitution reaction mechanisms. Now what we're going to concentrate with this particular topic, concentrate on with this particular topic is types of nucleophilic substitution and types of elimination reaction. So nucleophilic substitution, and this is displacement of nucleophiles, just almost as a reminder, because I think Dr. Ball's covered this with you. We have a substituted carbon bearing a leaving group called Y. We'll maybe talk about the nature of the leaving groups as we go along. An incoming nucleophile, X minus, it doesn't have to be minus, the nucleophile can be neutral, and we've met elements of that when we talked about amine chemistry, but it does have to have a pair of electrons to act in a nucleophilic way. That is going to attack this system and displace Y. Y needs to leave or wants to leave the system, and X has a tendency to attach to it. The equilibrium, if it's going to be synthetically useful, needs to be to the right hand side. Here's an example of a substitution reaction that you would have met at A level or equivalents. This is an alkyl halide undergoing a reaction with hydroxide ion to form an alcohol and bromine displacement. A more specific example, methyl bromide reacting with sodium hydroxide to form methanol and sodium bromide is a classic example. And there's a link with a little more background to the topic. We're going to look at nucleophilic substitution by a particular mechanism known as substitution nucleophilic bimolecular, SN2. Now the SN2 nomenclature, capital S subscript capital N 2, is strict because it differentiates between SM1 and SN2, and it is expected that you know that exact nomenclature. So here we have our reaction. Now this is showing not only nucleophilic substitution, this is showing an inversion of stereochemistry. So if we've got around the central carbon of our reactive species containing Y 4 different groups, which we will have if R1 is different to R2, different to R3, that will be a chiral centre. When Y leaves the system, SN2 reactions are characterized by an inversion of stereochemistry. This is known as Walden inversion, named after the guy who looked into the chemistry. So here's an example. We have a system reacting with potassium ethoxide. We have stereochemical inversion around the chiral carbon and elimination of iodine if Y is I. Here's an example. This is effectively ethyl iodide, but with a deuterium label. The deuterium label on that carbon now makes that carbon chiral, whereas in ethyl iodide it wouldn't be. We've got potassium ethoxide attacking the deuterated ethyl iodide. we can notice the chiral inversion because we can see the resultant 4 groups. If D was H, if the deuterium was H, then we wouldn't be able to look at this chiral inversion. And there's a link to the background to that. A technique of monitoring optical activity of molecules is by looking at the optical rotation of the solutions that you're doing the reaction in. This is how plane polarized light is rotated by a solution and analyzed by a polarizing filter. If you look at the links, you will find some information on this. So, what happens in an SN2 reaction, and why is it going to be different to any other reaction mechanism? So if we take our starting materials in our example mentioned on the previous slide, this is a typical SN2 reaction profile. We've got potential energy of the reaction plotted against progress of reaction. Now this is a device, this graph is a device for organic chemists to be able to discuss the reaction type with you, and for you to be able to discuss it as you learn about the topic. One can put value to potential energy in kilocalories per mole by doing theoretical calculations and measurements. So you can actually put figures to activation energy, the energy of the reactants, energy of products, and delta H for reaction and things like this. So they can become a real phenomena, but at this point it's just a point of discussion. Now what we see is a smooth progression from energy of reactants through a transition state to energy of products. So average energy of the reactants that we start with progress smoothly through energy of transition to products. If the reaction is exothermic, then delta H relative to the beginning of the reaction will be negative. It will be an exothermic reaction, and that will encourage the reaction to occur. At the top of the energy curve is the transition state. Now this is where the incoming nucleophile and the outgoing leaving group haven't quite decided what to do. There's a balance of incoming electron density and outgoing electron density, and that progresses smoothly. Imagine from the approach of OET to the carbon and removal of the iodine. That would be a smooth progression and therefore a smooth energy transition. And then chiral inversion results because the stereochemistry has been flipped, and potassium iodide is the product along with the ether. The rate of reaction would be responsive to the starting material and would be responsive to the incoming ether solution. Therefore, that's why the reaction mechanism is called SN2, because it's a bimolecular reaction. And there's a link there to that information. What we're going to do now is talk about the progression of reaction rates and the nature of the reactivity of sequentially substituted alkyl halides. In this case, it's a series of bromides. It could be equally a series of chlorides or iodides. A similar sort of progression would occur, or indeed with other leaving groups that behave a bit like halides. So here we have methyl bromide, ethyl bromide, isopropyl bromide, and tertiary butyl bromide. You can put the IUPAC names to those molecules. Karen would have Dr. Ball would have covered that with you. Let's look at the relative rates of reaction. So with methyl bromide, the absolute rates of reactions have been determined, and then we've taken the relative rates of reaction with respect to the least substituted halide. So if we make the methyl bromide rate 1, then relative to that, the ethyl bromide is less reactive. If we increase the substitution around the carbon bearing the leaving group, the bromide, you can see that the rate of reaction goes down again. And this is because of steric hindrance around the central carbon, blocking the approach of the incoming nucleophile that displaces the leaving group, i.e. the bromide. However, when we look at the tertiary bromide, you'll see that the rate jumps back up considerably. Now, that really shouldn't happen. So something unusual is happening with this heavily substituted bromoalkane. This is an inconsistency. The other thing is that this reaction is found to have a different rate equation. It's found to be dependent only on the concentration of the organohalide. There is a shift in the reaction mechanism for this particular compound, and this is known as an SN1 reaction. So what we're going to look at now is an SN1 energy profile and the characteristics of that. So here we have a heavily substituted organoiodide. It's got an ethyl group, a methyl group, and a tertiary butyl group on it, so this is really quite heavily substituted. We're going to attack that halide with, let's say, aqueous potassium hydroxide. Now, hydrolysis of that iodide should occur, and we should get an alcohol out of the reaction, but it's not going to progress how we think so far. So we know about an SN2 reaction. This reaction is going to proceed in a different fashion. Its profile is going to follow this curve. We're going to find that there are two transition states and a low point in the reaction of a stable carbocation intermediate. At this position, what happens is this. That halide is more inclined, because it's heavily substituted and the ethyl, methyl and tertiary butyl groups are all competing for space and pushing against one another, the inclination of that material in an aqueous basic environment is to actually ionize first. To ionize, it has to extend the carbon iodide bond in the solvated environment. That's what gives rise to transition state 1, which we're not going into detail about what that is, but effectively it's the extension of the carbon iodine bond without intervention of any incoming nucleophile. It gets to a point where the iodine leaves and we get a distinct stable species known as a carbocation. This carbocation then undergoes reaction with an appropriate incoming nucleophile, in this case the hydroxide ion, with its pair of electrons, and the reaction proceeds to the alcohol. Now, look at what's happened in terms of product. We have equal amounts of a pair of chiral alcohols. This is also why the substitution pattern on that iodine, organoiodide, was chosen. Ethyl, methyl, tertiary butyl, and then the iodine will give 4 different groups, therefore the starting material is chiral. When we do the reaction, we find that we get an enantiomeric mixture with no net chirality. This solution, the resultant solution, does not affect plane polarized light. In fact, what happens is the plane polarized light gets affected by one alcohol and rotates in one direction, encounters a molecule of the other alcohol and gets rotated back, and therefore the net polarization is 0. and this is because of an equal 50-50 balance of the alcoholic product. And the reason this happens is that the carbocation is planar. The central carbon has a p orbital. Effectively, the carbon is sp2 hybridized. It has a vacant p orbital looking for a pair of electrons from an incoming species. The species is flat, therefore the OH group can attack from above as equally as from below with no differentiation, and therefore we result in two enantiomeric species. This is a racemic mixture, and you've met racemic mixtures with Dr. Ball before. Okay, we're just going to stop there and recapitulate on what we've done. We've talked about the SN2 reaction mechanism. This sort of nucleophilic displacement is something that you're very used to, because you would have done that at A level, hopefully with a good teacher. It would be in A level textbooks. Probably have talked about the SN1 reaction, but maybe not in as much detail as we've done here. We're just going to take this idea a little further and talk about other things that may influence whether something undergoes SN1 or SN2 type nucleophilic displacement.